G'day chemists. So today we want to talk about reversibility of reactions and how that relates to the ideas of collision theory, in particular activation energy, how this all sort of comes together. So by the end of this, we want to understand the link between reversibility and activation energy, okay? We'll be able to do that when we can look at a reaction profile and justify our decision whether or not it's a reversible reaction based upon that, based on the way it looks and the characteristics of the reaction profile. So here's your vocabulary. If I can just get you to write this down, pause the video, write it down. We'll have this to refer back to as we move through the lesson. So just quickly remember that EA is our symbol for activation energy. We see on the graph here. This here is a reaction profile, an energy profile. And let's have a look, right? So first we start at the reactants, we go up to our activated complex, and that's where we've hit the activation energy, but the activated complex is when all of the particles are broken apart and in the right orientation to react or to collide with enough kinetic energy. And then it moves down, and this is a what's that, positive, so that's going to be an endothermic reaction, but it could be an exothermic reaction, the same sort of deal, just switch it around. So we start here, we add energy to it, we hit the activation energy, and it goes down. If we reverse the reaction, we actually see that here we have the activation energy of the reverse reaction. Now, the activation energy of the reverse reaction is equal to the activation energy of the forward reaction plus the enthalpy change. Okay, so that's important to know. And again, EA is our activation energy. So, this is related to reversibility in a pretty concrete way. So let's first look at a non-reversible reaction. Now, if we start with A plus B goes to AB, the forward reaction, the activation energy is going to be quite low. And this means that many particles have the energy to react. Okay, and we see that here. We've got a low activation energy going this direction. Okay, so lots of them are going to be able to react, and the products are more stable as well. Like the second part's not always true, but it can be true. Products are more stable, which means there's less bond energy in the products than the reactants, and that gives us an exothermic reaction. Now, this one over here is an exothermic reaction. So, away we go. And that's pretty straightforward. Now, the reverse reaction, the activation energy is relatively high, and that relatively means comparatively to the forward reaction. So colliding particles do not necessarily have the energy to react. They might still bump into each other if it's a solution or a gas, but they won't have enough energy to react. Reactants may be more stable than the products, so less bond energy there. And here's going backwards. And here's the thing, that is why this reaction will go to completion. So the activation energy for the forward reaction is easily achieved. So the reactants keep bumping into each other and colliding and reacting. Whereas going backwards, they don't reach that activation energy. So they're less likely to collide with enough energy, and eventually they'll use up all of their reactants in the forward reaction, not the reverse reaction. So it'll go to completion. Reversible reactions, on the other hand, and here we see it's A plus B, both directions, double arrow, goes to AB. And we see here our two reversible reactions. Can I get you to just pause the video here and write down what you think it is about those, before we move on, that makes them reversible? What's the difference between this and our non-reversible reaction right here? So I'm assuming you did what you were told, and we'll see how we go. So, if a reaction is reversible, that means it has enough energy to proceed in both directions. So what does that mean when we look at the energy profile? What it means is that the difference between the activation energy for the forward reaction and the reverse reaction is actually not that large. And here we can see we have a very small activation energy going this way and a small activation energy going that way. But it's not that big a difference. And here we actually have quite a large activation energy and a large activation energy going in the reverse reaction. But the difference between the two is not that high. So what that means is this one will require quite a bit of energy input to get it happening, but if it's happening at a high enough temperature, it'll happen in both directions at the same time. This one doesn't need as much energy to happen, so it'll happen in both directions, just at a lower temperature. So the enthalpy is actually not a large value. And that's actually one of the differences. So the enthalpy for a reversible reaction is a small of A, and that's because of the difference, which causes a change in activation. So the difference in enthalpy causes a change in activation energy from the forward to the reverse reaction. Hope that made a lot of sense. If you have any questions, put them in the comments below and we'll get back to you as soon as we can. Don't forget to subscribe, hit the bell so you can keep up with everything we're doing, and yeah, thanks for watching. Bye now.